A continuous random variable, defined informally, is one which has probability 0 of taking any particular value, but there are open intervals a, b which have positive probability. So, for example, a random time would be a continuous random variable. So if t was the amount of time after 12 p.m. until a company gets its first customer service phone call, t would be a continuous random variable. And that is because the probability that the first phone call takes exactly 1 minute, and we mean exactly 1 minute, so 0.0000 on forever zeros minutes is impossible. We could think of it in one way as it's impossible to measure that, but also that's so incredibly precise that there's no way that you're going to get something at exactly that time. There's always going to be some small error, but there has to be an error there. So what if the first phone call came at a minute and 0.000001 seconds, for example? Then it wouldn't be at exactly 1 minute. And that's why we say there's a probability of 0 that it's any particular value, because it just can't be that precise. But if we said the first phone call is going to come between 1 minute and 1 minute 5 seconds, then if it's around like 1 minute and 2 seconds and something, we can measure that, right? So there's a chance that it lands between a minute and 5 seconds. So that's sort of the way you want to think of a continuous random variable. And continuous random variables have a PDF, or probability density function, which is similar to the discrete random variables PMF. But instead of sums and adding up over all the different values that a discrete random variable could take, we integrate over the open intervals that the continuous random variable might land in. So the PDF is a function f which satisfies the probability that x is in a set A is the integral over A of f of x dx. So let's look at an example. X is a continuous random variable with PDF f of x equals 1/2 x for x between 0 and 2. Find the probability that x is between 1 and 2. So the event that x is between 1 and 2 is equivalent to the event that x is in the interval 1, 2. But you won't usually rewrite the events this way. However, it does agree with the notation that I've written above. So the probability that x is in 1, 2 is the integral over the interval 1, 2 of f of x dx, which means to integrate from 1 to 2 of f of x dx, and f of x in this case is 1/2 x dx. From here you just do standard integration, so it's 1/4 x squared evaluated from 1 to 2, which is 1/4 times 2 squared minus 1/4 times 1 squared, or 3/4. So the probability that x is between 1 and 2 is 3/4. Now, since the PDF represents a probability, it must satisfy certain properties because it is a probability. So since probability is always non-negative, a PDF must also always be non-negative. For example, f of x equals x cannot be a PDF because f of -1 would be -1, and that's less than 0. Also, a random variable satisfies that the probability that it's a real number is 1. So the integral from -infinity to infinity of f of x dx must equal 1, either by being a function that has positive value everywhere that integrates to 1, or it's 0 everywhere except for, say, on some finite set. So a function like f of x equals x where x is bigger than 0, and f of x equals 0 when x is less than 0 is not a PDF, even though it's always positive, because the integral would be infinity. However, a function such as f of x equals x when x is between 0 and square root 2, and f of x equals 0 otherwise, is a PDF. So that would look something like this. If we had the x-axis and the y-axis, then from 0 to square root 2, we just have a line like f of x equals x, and otherwise the function is 0. So it's 0 here, it's 0 here, just 0. So the only area is under this part of the curve. And that area has to be 1. So we can check it if we integrate from -infinity to infinity of f of x dx. Well, the function is 0 everywhere except for on the interval from the 0 to the square root of 2. And on that interval, it's just x. So we have the integral from 0 to root 2 of x dx, which is x squared over 2 from 0 to root 2, which is root 2 squared over 2 minus 0 squared over 2, which equals 1. So since that value f of x is, that function f of x is always bigger than or equal to 0, and it integrates to 1 over the entire real line, that is a valid PDF for a random variable.